Goes beep, beep, beep. And then we dive in. Thanks so much for showing up for your learning. Let's get on with it. Solving inequalities. So, Gavin, you have a lot of experience solving equations, right? Yeah. And we're going to apply those same skills to solving inequalities, but we're also going to use like a graphical method today to understand that a little better. So let's go. Let's take a look at it. We want to be able to write intervals from a number line. We want to be able to graph intervals on a number line. And also, here it should also say, use interval notation and inequality notation. So the two notation systems that we looked at yesterday. Okay, one moment. All right, so let's take a look at our examples today. So we can work algebraically, and we're going to look at that tomorrow. But today we're looking at graphically. So this may involve making a graph or working from a given graph. Over here, we're given f of x. So here is our function, f of x. And we are asked, when is f of x greater than 0? So that's pretty straightforward, right? We have a greater than sign, but it's not greater than or equal to. So we have these 2 points. Anything out there, it's greater than 0. And anything out there, it's greater than 0. And in this realm in between, the function is clearly less than 0. So if we wrote it this way, minus 2, 5, that would be our interval notation for x. Sorry, not that. No, that's the interval where it's not true. Yeah, good. I got some confused looks. Negative infinity to minus 2, and we also have the union of that with 5 and positive infinity. These are the areas where the function is positive, greater than 0 but not equal to 0. Yeah.
Would it have square brackets by the -2 5?
No, because we want greater than 0, not greater than or equal to. So it's like excluding those values where the function is exactly 0, and the function's exactly 0 here and here. So we would use round brackets in both cases. Okay, so that would be that notation. If I were to say x is of the reals, and x is both, we could say x is less than minus 2, and, or sorry, I should say or, because it's the union of those two things, or x is greater than 5. And those are the times when the function is positive. Okay. Another example here. In this one, if we have the function is less than or equal to 0, I am looking for y values that are down here. And so I have this realm and this realm over here. So I would say on a number line, if I were to give you the solution on a number line, it would start there at minus 2. Closed dot because we are including minus 2. And then we would have this realm in between 1 and 3. And we would include all of those. So we would have negative infinity to minus 2. Here we need the square bracket. And then we have the union of that with 1 to 3, closed bracket. Or x is of the reals, and x is less than or equal to minus 2, or 1 is less than or equal to x, which is less than or equal to 3. And those realms are okay as well. People are busily writing things down. That's cool. I'll give it just a second. Okay, keeping going. All right, this one is a little trickier. If we wanted to have f of x be greater than or equal to 0, I have to note, like, there's my 0 intercept, and it's all of those values that way that work. And then also starting at this asymptote and going that way, all of those values are greater than or equal to 0 as well. So here, and I've been asked to include 0, so I would have round bracket, negative infinity, all the way to 1/2, positive 1/2, and we include 1/2. But then I also have this asymptote at 2. F of x, we have like x cannot be equal to 2. That's a restriction on this function. So we can't include 2. So we would say round bracket 2 comma positive infinity. And we would have the union of those two realms. And if we wrote it like you could say x is less than or equal to 1/2, or 2 is less than x. These two would also be saying the same things as those above. If we wanted f of x is less than 0, then we have this range that goes from 1/2, not inclusive, because this one is not less than or equal to, so we want to exclude. We are excluding this point here. So from 1/2 all the way to 2, non-inclusive would describe the realm where this function is down there, negative. This example makes sense? Slightly trickier? Okay, cool. Let's keep going. If we had, it's just the same one this time. What if we are not given a graph? What should we do? And they say, solve it, and you want to do it graphically. Yeah?
Was the last one the same one?
Yeah, it's just the same example.
It's a little bit different, right?
Is it?
Yeah, we have a fourth on our sheet.
Oh, yeah. It's slightly different. It's like effectively the same thing. It's just the asymptote is moved over just slightly.
Yeah.
Yeah. I want to say that that's the same example. I want to move on to the example I made for today because it's much more interesting and we get to flex our muscles a bit. Suppose we want to know when is 4 times x to the 4 plus 3 times x squared plus 23 times x less than 15 times x cubed plus 15. How do you suggest we start here after you've copied down the example onto a piece of paper for yourselves?
Factor?
Oh, we should factor. That's a good idea. Should we just go ahead and factor the different sides independently? Oh, Nathan didn't like that idea. What do you want to do first?
Move multiple one side.
If you were solving this as an equation, moving it all to one side and setting it equal to 0 would be your strategy of choice. And that doesn't change. We're going to use the same strategy. Okay, so which side do you want to send things to? The left side or the right side? You're going to send things to the right side? I'm glad you said that because sending it to the left side is much nicer. But if we send it to the right side, then we'd have to divide by -1 and flip the equation. Let's send it all to the left side. Okay, let's do it the easier way. So our first step is to take away 15x to the 3 and take away 15 from both sides. We have no like terms over there, so I'm just going to list it about where it's going to land. And we subtract from both sides the inequality. When we subtract things from both sides of an inequality, do we need to flip our alligators? No, only when we multiply or divide by -1. So let's rewrite 4x to the 4 minus 15x to the 3 plus 3x squared plus 23x minus 15 is less than 0. Okay, so that's a good first step. Now, if this was an equation, it could tell us where the function was exactly equal to 0. But before we get there, what degree is my function? It's 4th degree. Is that even or odd? Even. What can you tell me about the end behavior of this function? Yeah, we're doing this dance. Okay, so as x goes to -infinity, the function goes to positive infinity. And as x goes to positive infinity, the function goes to positive infinity as well. So we're this dance. Okay, so we know that we're doing something like this and something like this with this function. So our values where we're going to be negative must be somewhere in the middle. Okay, they must be in between the infinities. Okay, so now we know our end behavior. Let's go ahead and find where this is exactly equal to 0, because we're going to be able to produce a great sketch once we've done that. So how do we go about doing that? What values of x will make this exactly equal to 0? Remind me how we do this. This is Unit 1 stuff. It's like this one and this one. Yeah, it has to do with these coefficients is really what we're starting to look at. And this is going back to remainder theorem and factor theorem.
We long divide the other ones with them?
We're going to need to find something to long divide this function by.
4 minus 15? No.
No, we're going to look for a 0. Okay, we want to find one of our zeros, and the convenient ones to check are if this is this one we call, say, C, and this one we call, say, A. Okay, we're looking for the factors of C divided by the factors of A. So what are the factors of minus 15 that you might want to try first?
3 and 5.
3 and 5, or anything easier? You'll like it. One of the, you didn't name one of them that's in there, but there's an easier one to take out. 1. Just check 1 first. Plus or minus 1 is almost always an option to check. Will plus or minus 1 produce a 0 here? If x is 1, what's our function equal to here? 4 minus 15 plus 3 plus 23 minus 15. It's 0. So you're going to be highly suspicious. Maybe 1 works. Okay, so check it. And in this case, you just add up your coefficients because inputting 1 for x just returns your coefficients. So we know since when x equals 1, we'll call this f of x equals 0. We know x minus 1 is a factor. Okay? Because we must have a 0 there, so we know this is one of our important points. And that means x minus 1. So that's what we're going to divide into this function. So we write it out. X minus 1 long divide into, if you're using synthetic division, I salute you, but I don't understand you. So that's fine. You can do that, but I do this. So let's go. We're going to long divide in here. So I'm going to multiply first by what? Gavin?
Why wouldn't you use synthetic division?
Why wouldn't I do synthetic division?
Yeah.
Because it doesn't work in all cases, and it feels like mathemagic to me.
It's not actual math.
It's not that it's not actual math, like it's actual math, but because it leaves the realm of kind of what I can understand at every step what I'm doing and abstracts it, and then it like returns something back to me that I then use, I'm uncomfortable with that when I can't like relate, okay, this line is equal to this line is equal to that line, and I can verify it and find my errors easily. So I prefer a method like this where I'm just doing long division and I understand long division. Canal says I multiply by 4x cubed. I multiply this by this and write it down here. 4x to the 4 plus 4x cubed. Sorry, no, minus 4x cubed. Okay. Then I go ahead and put this in brackets and recall that I'm subtracting here. Kunal chose to multiply here by 4x cubed because it would knock out our x to the 4 term. That returns 0 down here. They're gone. And then minus 15x to the 3 minus 4x to the 3 is minus 11x cubed. Okay. Minus a minus is a plus, so we just want to get that right. And when I notate in a really clear way this way, I avoid errors. So that's why I choose to do it this way. Now I'm going to multiply here by minus 11x squared. Minus 11x squared multiplied by this one gives me minus 11x cubed plus 11x squared. Okay. Now I put that in brackets and I subtract, and I also bring this 3x down here, so I have plus 3x squared to subtract from. These get knocked out, they're completely canceled, and minus positive 11 is minus 11, so 3 minus 11 is minus 8x squared. So now I need to multiply here by minus 8x, And so I multiply that by that, and I get minus 8x squared plus 8x. And I bring this 23x down. So I have plus 23x here. I put this in brackets, and I minus all the things. So that gives me 0. And 23 minus 8 gives me 15x. And I get this very happy feeling when I drop down this minus 15 because I see that I will have 0 remainder, which means we're on the right track. So I multiply here by plus 15, and then I get 15x minus 15. I get a 0 remainder, and I put the happy face in there because I'm very pleased to see the 0 remainder. So what we've found out is that this all is equal to x minus 1 multiplied by all that stuff. 4x cubed minus 11x squared minus 8x plus 15. All of that is less than 0. So this is you would get to the same point with synthetic division. You would have this line, and then you could write that line. I just find it harder to find my error inside synthetic division than inside long division. So I write it this way. So now that I know this, I still have more factoring to do. What factors should we test now in here?
-1.
You want to try -1?
Sure.
So 4 times -1 cubed gives me -4 minus 11 plus 8, because we're minus 8 times plus 4. Seems like we're a little heavy, but on the negative side. We already tried 1. We already divided 1 out.
No, what do we get?
Huh?
Do we get?
Do it again. We can take out the same factor twice? Really? Can you? Sure you can. Yeah, it's in there twice. Look at 1 again. 4 minus 11 minus 8. So I would just do my minuses together and my positives together. 4 plus 15 is 19. Minus 11 minus 8 is minus 19. 19 minus 19 is 0. 1 works again. Okay, so we're going to end up with some kind of bounce root there, because it's a squared root. It's a root twice. So we're going to go ahead and divide it in again. So we have x minus 1 dividing into 4x cubed minus 11x squared minus 8x plus 15. And we multiply by 4x squared here. We get 4x cubed minus 4x squared. Put that in brackets and subtract it. You end up with 7x squared, but it's negative. We drop down the minus 8x, and we multiply here by minus 7x, so we get minus 7x squared plus 7x. When we subtract all those, these are 0, they go away, and this gives us minus 15x plus 15, and that again makes us very satisfied because we multiply here by minus 1, and that returns a 0 remainder again. We get to do the 0 remainder dance, and we're pleased. Yay. Okay, so now we can write that this is equal to x minus 1 squared multiplied by 4x squared minus 7x minus 1. All of that is less than 0. Now, yeah?
How come it, on the last step for the division, I'm not sure I got it. It went.
When we multiply by minus 15. Thank you. Thank you for catching my error, because I'd be really frustrated. There, that's much, much better. Thank you very much. Okay. So now, that's markable, but I'll get it in a minute. Eva, if you want to mark it, you can. So now we have this is true, and this is a quadratic. How are you going to factor this quadratic? Are you going to find a factor the same way that we used to, same way we just did in long divide, or are you going to factor it as a trinomial? Everyone's going to trinomial factor, that's fine. You can use long division here, no problem. You just have to go ahead and hunt and find that 3 works. 3 will work, and you can find that. It's one of the factors of 15. Okay, so if we're going to factor this one, 4x squared minus 7x minus 15, let's write it down. Somewhere in our rough work. If you're going to factor this one, we want to multiply to 4 times minus 15 and add to minus 7. 4 times minus 15 is minus 60. What are the magic numbers that does this? '60's factor rich. So there's a lot of different ways to do this.
12 and 5.
Yeah, negative 12 and positive 5. So once we found these numbers, we can rewrite this as 4x squared plus 5x minus 12x minus 15. See, Gavin, I always like methods like this. Like there's like other methods for factoring these that are totally valid. They work, but they involve writing things down that aren't true. Like pretending that this a value is 1 and sliding it over and making that 60, factoring it, and then doing some special thing. This is like hacks, yeah. I call them mathemagic. When it's just like answer pop out, I use answer. Whereas I can see that minus 7x is those two things that I just split apart, and now I just factor by grouping, which is all very comprehensible to me. So I factor out an x of those two first terms, and I get 4x plus 5. That's just factoring that group. And then this group I see minus 3 is the factor, and we get 4x plus 5. Common binomial factor appears there and there. So we have this is equal to 4x plus 5 times x minus 3. Okay, so now we just going to transplant that up into the main flow of our solution. X minus 1 squared times 4x plus 5 times x minus 3. And as I was telling you, yeah, x minus 3 is the little factor that I baked in there. Okay, so now, how do we use the information that this presented us to create a nice sketch?
Find like the roots, and you know the first one's a bounce root.
Yeah, we know this one's a bounce root here. We bounce. But I don't know that that's like kind of the first one, because I'm going to work from my end behavior to the roots on the edges first to create a sketch. Yeah, so there's one at 3. And there's one at, what's the root here for 4x plus 5? Negative 5 on 4, or negative 1.2. Okay, negative 5, sorry, 1.25. So we're 1/4 of the way from negative 1 to negative 2. So there's our roots. And if I just follow my end behavior, I'm doing something like this. I go through there. Here's a point you can find with calculus. We're going to come up here. We're going to bounce. Here's a point you can find with calculus. And then we're going to come up. And these are cut roots, so they just go straight through and go up. So there's our sketch. Now that we've got our sketch, it's now nearly trivial to just demonstrate what the ranges are where this thing is negative. Sorry, where this thing is less than 0. Yes, so negative. So we note that we are less than 0. So that means negative 1.25 is less than x, and it's less than 1. And or 1 is less than x, which is less than 3. We've got these two realms where it's negative. We don't want to include this bounce root because exactly at 1, it's exactly equal to 0. It's not, therefore, less than 0. Because we are less than, not less than, or equal to. Yeah?
Are we always finding it when it's negative?
No, you can find it when it's positive too. Here, when it's if I said greater than or equal to 0, you would say x is less than or equal to negative 1 1/4, or exactly 1, or greater than or equal to 3. Okay? And if I use like interval notation, I would say non-inclusive, negative infinity to 1.25, but negative. Oh, sorry, no, that's not right. Not inclusive, 1.25 to 1, union 1 to 3. There. Yeah. Because between here and here, and between there and there, but not including that one. So I wanted that little more challenging example because reviewing long division, very useful. Reviewing how do we find those darn factors? Test 1 always. And don't fear testing it multiple times. It might be a factor twice. So I would always test 1 first and then test -1 like you suggested, Charlie. And then test, in this case, 3, -3, 5, -5. And then if I still need to go hunting, I'm going to have to put those over 2 and over 4 because we had this 4 there as our leading coefficient, which might have made it more challenging, but in this case it wasn't. And then if you still can't find the roots, you're pretty much in a solved by Desmos situation because the cubic formula, we would find quadratic roots when we can't factor with the quadratic formula. The cubic formula itself is a page long and we don't teach it. So you're basically in solved by Desmos territory at that point, and you won't see those examples in this class. Okay, thanks for locking in, everyone. Carry on with the practice, which is organized for you here. And there is a, so focus on the practice in the textbook and use Desmos to check your answers. Any questions? Hit me up with your questions. Bye for now, everyone.